modern math. Hello.
Don't really know how modern it is, but hey, here goes. So my name's Ben Agre. I'm a student at MIT. I just sort of do random things, and I figured I'd try and talk to you a little bit about some random crypto you may or may not know about. Really, I just wanted to buy a ticket. However, this plan was foiled when they let me speak, and it's really, Anyway, so what this talk hopefully is, with any luck, it'll be an introduction to some public key crypto, Diffie-Hellman, not RSA, some random algorithms that you might not have heard of, some you may have, some intuitions behind those algorithms, hopefully, and why they're a little bit different than what you might know. And what this is hopefully not is me lecturing for an hour about math. It could very well turn into it, but if, and a list of algorithms. I don't want you to just list off things, you have no idea what's going on, a detailed workings of how the pairing function works, or a Q&A about something you wrote. I don't know it, I don't care about it. And so the layout is pretty simple. We're going to go just some basic introductions. Then we're going to go into this theory called gap groups, which is just sort of this black magic thing. That's awesome. Then the BLS signature scheme, because I can't pronounce the last guy's name in that one. And two things called predicate encryption. Predicate encryption is a little bit different than how you actually normally think about cryptography, because it does things in a little bit of a different way. So first off, there's lots of... When I say new crypto, I'm actually pretty much talking about the past 10 years mostly. Since when you think about RSA, Diffie-Hellman, and most of the things you use every day, except for AES, they're from the early 80s usually. AES is actually from about 98-ish, so that's pretty far ago still. But like in the past 10 years, and most of what I'm talking about is in the past 5, there actually has been some AES cryptanalysis. It's not going to be viable yet, but it's started. Side channels actually matter now. Things that we never cared about before, like Intel, how it actually changes the flags from the AES encryption function, is actually leaking information. And there's currently something called the SHA-3 hashing competition, where there's so many new hashing algorithms. There's new ways to think about how you would do a compression function, new ways about how you actually construct things, stuff we haven't touched since the Merkle-Domgaard compressions, which were in like MD2. Now people are starting to look at them again. We also have homomorphic encryption, which is this thing where you can work on encrypted data. We have order-preserving encryption, where I can encrypt two things and compare them. I can figure out if they're less than, greater than. I can preserve ordinality between an encryption. And finally, pairing things. We're going to deal with the pairing things. We're mostly going to deal with something called a pairing function. But before we start talking about that, I want to talk about some math. So we're going to go over some notation. So first, we're going to talk about a Galois field or a finite field. It has a bunch of properties, but very simply, it's mod. So when we think about it, first off, it's defined as GF to the n of a prime raised to a power. And what it essentially is mod. So if you have a GF field of 23, just think of every multiplication, addition, all is just mod 23. So 20 plus 2 is 22. 22 plus 2 is 1, because 24 mod 23 is 1. Now, we're going to go over next to what's called a generator. A generator is, as Wikipedia defines it, a primitive element, which is something that essentially means I can generate every element in this group. So we have an element G in G, and I understand that's a bit confusing, and people don't like me, it's fine. And we do this by taking G, the little g, to a power, and each power will give us a new element in our big group G. So we can see this fairly easily in an example. 3 is a generator of 7, 2 is not a generator of 7. If you look at the table, you can see that 2 will start rolling over. It'll go 2, 4, 1, 2, 4, 1. In 3, it'll go 3, 2, 6, and at the end, you have every item in your big G will be generated by a random element, by taking 3 to some power. So, how we usually pick our groups. First off, does everyone understand this whole thing about how a generator works? No. What's confusing? All of it. Awesome. So let's take a step back. When I raise 2 to 1, you get 2, correct? 2 to 2, you get 4. 2 to 3, you get 8. What's 8 mod 7? What is it? 1. So if I multiply that by 2, I get 2 again. So I start cycling back around. If I raise 3 to every power from 0 to whatever my group element is, in this case 7, it will give me a different number. It won't cycle till you get to 7. Does that make more sense? Yes. Awesome. That's what the table was trying to explain. No, please, if you have any questions, I'd love for you to interrupt me. I can make assumptions, I can mess up. I would love to hear what you want to know about. So first off, we're going to go how we pick our groups. And after this slide, we start stopping with the whole math thing for a while. So we choose a random prime. We multiply it by 2. We add 1. And then if that's prime also, there's a very high probability that the first prime we picked is going to be a generator of our second prime. We don't need many of these. You can Google generators for Diffie-Hellman groups, and they're all defined. You can grab one randomly online. If you're doing GITs, you will actually see one that I picked randomly and doing this exact thing. And pretty much, if those 3 cases stay true, then you know it's going to be a generator. So first off, now we have to go into one thing. A lot of crypto that you actually use, and a lot of the newer stuff, is built on this something called the Diffie-Hellman problem, which can be broken down into like 19 separate subproblems. Okay? We care about 2 of them. Well, we care about 2.5 of them. So first off, we have what's called the computational Diffie-Hellman problem, which says, given a g to the a and a g to the b, can we get g to the ab? So what if I take g to the a and multiply it by g to the b? What will that actually give me? Bingo. Hence, if I can solve this, and I can solve it for any version, it means I can solve the discrete log problem. This is all assuming computational Diffie-Hellman's hard. Decision Diffie-Hellman is given a g to the a and a g to the b, does g to the c, another number I give you, which has a 50-50 probability of being g to the ab, equal g to the c. Okay? Now, do people understand those 2 concepts? Because these are the 2 most important concepts I can give you throughout this whole talk. Does anyone have an issue with it? Okay. Well, yeah. So now we have to think about hardness for a second. If DDH is hard, the decision Diffie-Hellman problem is hard, then it means CDH has to be hard. Because if you can solve CDH, it means you can just compute what the answer to DDH. If CDH is hard, it doesn't mean DDH is hard. So we can check things without knowing whether or not we can compute it. There's a bunch of groups where DDH is hard, or is easy, but anyway. So now we make the magical easy button. Non-polynomial time to our current knowledge. You can do it, you can actually brute force it out. It's just we don't know a good way we don't know an efficient way to do it. Does that make sense? That actually comes up in the next slide. So what a gap group is it makes the decision Diffie-Hellman problem easy, but the computational Diffie-Hellman problem stays hard. So what that pretty much means is I can now compare things without knowing what they are. This is the thing that we're going to keep on going through. This is absolutely freaking awesome, because it allows us to do all these things we never thought possible. And we also have something called non-degeneracy, which we don't really care about, but it pretty much says we can create a generator from our generator. So that is a bit of a what the fuck moment. The gap groups work by something called a bilinear pairing, which means if I get 2 elements out of group 1, or 1 element out of group 1 and 1 element out of group 2, I can map them to another group inside something called GT, and it'll keep these things. So more formally, it means for every A and B in G1, if G is a generator of G1, G to the A, comma, G to the B will map to H of AB, which will equal to G times G to the AB, which equal to G to the A to the B. Okay. Does that make any sense to anyone? Awesome. What's up? Big G is the group, it's your field. It's a so all times, big G represents my field, little g represents my generator. I know it's a bad notation to give a talk on, but it's the one I've usually seen. So I figured instead of making up my own, I'd try and make it so if you decide to read something, it could be useful. So let's go over this for 1 second. Decision Diffie-Hellman's easy, so we can actually now check if g to the a times g to the b equals, well, g to the a and g to the b equals g to the ab. So we can actually distribute those in any way. So if we look at the first one of e of g to the a and g to the b, it's equal to the second one because e of g and g to the ab is 1 times g to the ab. So we can quickly figure out whether or not this becomes true. Does that make more sense? Where are you getting, somebody who's stuck, please tell me where you're stuck on. Please tell me what the issue is. I'd really love to know. Oh, okay, I'm sorry. What's up? Why is it applicable? That's 2 slides down. What this means is this equation holds true, and we'll get to Atlas's question in about a minute. And that just means non-degeneracy is the fact that the mapping does not change the generator's ability. We can create a new generator. So now we get to the cool part. All the math is kind of boring. I'm sorry. I just like it because it lets you see something. So BLS, I don't know how to pronounce their names, is a really short signature scheme. Now, why the hell do you care? So think about signing something with RSA. RSA PSS with CHOS 256 ends up giving you about a 384 byte key. So if I want to sign a text message, I can't. If I want to sign low bandwidth constraints, if I want to do any of these things, I can't. With BLS, for the same security margin, it's 32 bytes. So in a walkie-talkie, in something that's not going to work out well, in something that's going to have bad MTU, I can then keep things in really small chunks. I can make things work, and I can do it very small. As well as the fact of RSA padding's freaking complex. This is the padding for RSA PSS whenever you want to do anything, which is hard, and there's this whole padding oracle thing, and there's massive issues if you just go do the RSA. So do people now understand why they care, or at least one part of why they care? There's a bunch of other reasons, but we'll get to them later. And the really cool part is if you get the pairing function, it's actually really easy to understand. My private key is just some x below g above 0. Our public key is g to the x. We give that to everyone. Sign it. All we do, hash the message, raise it to the x. That's the entire signature process. It actually is a couple multiplications and one function, but it's actually a really simple process to see. So verification. G to the x gets raised to the outside. So our sigma, as we can see from 2 slides ago, is just h of m to the x. Now, I'm slow. So now think about it. All 3 of these equations are equal. And we are inside an elliptical curve, so we only need like 256 bits for the same as 3072. And as the higher we want our security margin, the better that margin becomes. Because elliptical curves get smaller at a much smaller rate than the hardness of any of the problems we use day to day. So if you want to actually see this, there's something called the PBC library. It's links at the end of my slides. And you can actually see them implementing this and using it. And actually doing things. However, I hate to break it to you, people don't actually like using BLS as much. Yes?
Yeah, I have a question about the statement you made a few minutes ago. You're saying that it wraps around quicker but doesn't degrade security. Why is that?
The issue still becomes how hard it is to solve the problem. Well, actually, what do you mean by wraps around?
Well, I'm thinking you mean that the number one target key is not that it's wrapped around. The groupings of your randomness will begin to repeat itself, right?
I don't understand your question. I'm sorry. You mind rephrasing it? So we define our security as like you have a some bit key. Am I close to what you're going for? So our security model is how quickly we can break that key. In RSA, it's how quickly we can factor it. In elliptical curve, it's how quickly we can find the point on that curve. Okay? So is that what you're asking?
Sort of. It just seems to me that you've got
Define wraparound.
Well, you tell me what you mean by wraparound.
The modding. Awesome. Inside the field, on an elliptical curve, you have some function of y squared equals x cubed plus something. Okay? It's harder to find a point on that curve because all your point is you're multiplying a scalar by it, and it's harder to find a point on that curve inside your field than it is in order to factor a number. Okay? It means it's a harder problem for us to solve currently. It's two separate problems that use the same strength notation. Does that make more sense?
It does, but I'm thinking about those big-ass computers setting up a 4D.
Yeah, I don't know what they know. Sorry. I don't know. They might have something, but fuck if I know. Anyway. So what we actually use if we want to do it is something called the ZSS short signature scheme, which is actually a lot faster. It's a bit more complex, which is why we didn't go over it, because I think that this makes sense to people. The algorithm for that is just weird. Anyway, and so we can actually see why it's faster is that last line. The BLS requires an extra pairing function, and pairing is slow. Pairing is a hard operation for us to do, but it works great for small areas. And this is stolen shamelessly from a survey on pairing cryptography that if you want to read about every frickin' pairing algorithm you could ever imagine, they will discuss it. And it will be odd. Anyway, so now we'll talk about predicate encryption. This is one of those weirder subjects. This is the thing that I really think is awesome about this because it has a lot to do with the cloud. So the predicate encryption is best defined as I don't want to encrypt my data, I want to search all my data. I don't even want to only search all my data, I want every one of my searches to be different. And I want you to be able to compute them, give me back an answer, and you not to know what that answer is. So the last thing was completely applicable. This is absolutely not. This is just really cool, I think. It has massive overhead. The ciphertexts are huge. It does great things. Yeah, no. And so that whole thing of cryptography is a safe, you can't think about it like that anymore. Cryptography is, in this system, you have to think of an entirely different threat model. So the best way I could describe it, I really can't make a good metaphor for it, I'm sorry, is your safe now has a bunch of windows, and you can hand someone a key to a window, and they can look in and see if there's something in that box. They can't tell you what's in that box, they can't tell you what window they look through, but they can tell you through that window they believe there is something in that box. Yeah, did that make any sense to anyone? What's up? That's fine. I'll try and go and I formalize that a bit more, but that's the best metaphor I can come up with. And so we're just going to go over what these things actually do. And if you read any paper, you'll pretty much see the same 4 things in it. Key setup, give me a key because the keys are ridiculously complex. Encrypt, giving a text and a key, give me back a ciphertext. Generate token. So tokens are a question. And the token is essentially what I'm giving to you to compute on. Why it matters. This is usually it usually gives a response back. In most cases, it's true or false. It's not always true or false, but for us, it usually is. So now we have to think of 2 separate models. Predicate encryption can either be public key or private key. But public key and private key have 2 absolutely different threat models to us as long as we're handing off our data. So we're going to tell you the story of KSW. KSW is a public key predicate encryption algorithm, which means you can encrypt something, send it to me, and I can have the same tokens work on it. People understand that? Yes? No? Maybe so? No. Okay. So you don't usually think about predicting things as decrypt. You think about it as does it equal? Okay? And so what you do to figure out if something equals is you give it a token, and you figure out what that token evaluates to. Okay. Oh, shoot. So let's meet our characters. Our fearless hero, Alice. She is our leader through this long and treacherous journey. She knows the keys. She can encrypt, decrypt, or query, essentially, and create tokens, which is how we'll have to think about decryption. Bob, her semi-trusted sidekick. He has a server farm. I don't know what that was, sorry. Anyway, that was the moose, more moose than ever, or whatever, I don't even know. What? Oh, go for it. Anyway, I'm going to go on with my talk. This is Bob, her semi-trusted sidekick. Bob has a server farm. Alice uses Bob for his server farm. We've all heard this story before. We want him to do work for us, and we want him to give us results back, but we don't want to tell him what they mean. So we kind of trust him, just not fully. We trust him to be, we'll believe he won't act badly, but we don't want him to know what he has or how valuable it is. And this is Eve, the evil bitch. Anyway, she's our attacker. She wants Alice's secrets. She can do many, many evil things in many, many evil ways. And now, let's think of an email relay or a protein folding or one of 1,000 stories. So I wrote the title as email relay. I meant for this case, it's biocomputation. We'll just ignore that one. So Alice sends Bob a bunch of work, and then she sends him a bunch of tokens. Bob is doing something like protein folding, mail forwarding. It can be pretty much anything. Alice is looking for a specific set of structures. Her structures are secret. She doesn't want to let Bob know what she's doing, what she's looking for. Why is she looking for it? Because Bob might be then able to steal her ideas, which not a good thing for a sidekick to do, but Anyway, or it could be she just doesn't have the same security. Eve decides that she can't attack Alice. Alice doesn't hook up her computer to the internet. Alice is paranoid. She's in a Faraday cage. Everyone, Alice is as paranoid comes. Now, instead, she doesn't attack Alice. She attacks Bob. In like a homomorphic scheme, this would be like, okay. But she now has a set of tokens. And way back when on KSW, what is KSW? What is the first line of this? Can someone speak loudly? Key is public. So what does that mean? Anybody can encrypt. But anybody doesn't actually know the tokens. So Eve now has the ability to encrypt and the ability to evaluate tokens. The predicates, which you deemed as private, aren't really private. Well, shit. This means that if I ever can actually take control of the tokens in a public key scheme, eventually I will be able to derive out the things, as long as I have some semi-computationally unbounded item. So what do we need to do then? This works great in the public key scheme. What's the other scheme we can make this as? Well, symmetric. So we have to introduce a new concept of essentially predicate privacy. Do we care? We can make him do more work. We can change the predicates, but we can make it so only we can generate the predicates. Think about Dropbox. Inside Dropbox, let's say you want to be ultra paranoid and you want to have a full ACL system, you want to do all this, but you don't want Dropbox to know why. You don't want Dropbox to know what files they're accessing, but you want to use their computing power because, hell, it's Dropbox. We can now set it up so Dropbox can run the predicates, can find the answers, but we can make it so that the predicates never look the same, so it can't easily figure out which predicates it's evaluating when. And you can then make tokens, predicates, and all this other fun stuff. But we essentially create it so that we only encrypt it, which is actually a really hard feat, and that finally got finished about 2009 by Shen, Shi, and Wooters. So this is actually the private predicate scheme, and the best way I can describe it is the other one is AES, this one's RSA, public key, private key, but this one introduces the theory of predicate privacy. We now have multiple targets in our system. We care about our cloud provider. Instead of believing that our cloud provider is entirely secure in a public key system, we now have to worry about their security. We now have to worry about different things along this chain. So how do we fix this? One way is to randomize the questions. We can make it so that no two questions look the same. If you want, there's slides on this later, but we can go over why they don't look the same. And to do this, we just change what's going on. Now, why is this different than homomorphic? Or actually, first off, does everyone understand the concept of predicate privacy? Okay. Does everyone understand how many more targets you can make? Okay. I guess. Anyway, we'll go back to other things. So, the other thing about this is predicate privacy now becomes one of those things of we don't actually do this on general text. When we think about predicate encryption currently, we can't do this normally. We work on some vector. We work on some item. That item's in magical, mystical land. But all it is a set of numbers. Bytes are a set of numbers, but we work on something called the inner product query. Anybody remember what that is from like 9th, 10th grade? Okay, neither do I. But anyway, the best way to describe the inner product query is all the way down here. Right there. So all that says is the last little thing is exit for each x of v times y of v, give me the value back. And as we go and homomorphic works on everything. It doesn't care. Everything's a circuit. Everything works. Now, we're going to go and discuss SSW a bit. And we're going to go on why it's so freaking complex. And then I'm going to ask you some questions. And I want to actually try and make this a dialogue about what you think about this. Because why the hell not? So first off, you see all these things? To encrypt, so, where's my, I apparently lost a slide. Whoa. I really lost a slide. I have no idea where that slide went. This is going to be way more interesting now. Anyway, yeah. So, try and keep as many of these things in your head as possible. What's up? Yeah, no, I believe it. I lost myself too. So we're not going to actually go on into why this all works exactly. We're going to go on very high level. So you see all these things? The generators in all of this scheme are secret. All of H is secret, and all of U is secret. So we multiply all these things together, and this is encrypt. You can try and keep as much of this in your head as possible. If you don't want to, don't worry about it. Now, so I just want to take notice of how H of U and GQ are related, because this actually matters later. To generate a token, we use inverses of themselves at times. So way back when, well, we use the the ciphertext is actually just that blob of math. But inside of our actual scheme, for each element in the vector, we have to encrypt 4 elements. And hence, it becomes a really nasty thing really quickly. To generate a token, we then have to do the inverse of each of these to try and get them to cancel out. So as we go through all of this, I know I'm not explaining it well because it's a lot of math. We have to go through and check each inverse. We have to go through and make it so later as we go on to this, it cancels out. Because most of these predicate schemes say is make it cancel out. And you can make things work this way. Because the query function actually looks really simple compared to these two. It's just this. Something times a product. C from way back over here is S times GY. S is some random element in G. G is a set of 4 small groups. And yeah, after that, we just make it go out. So this is actually it expanded, and I think this looks prettier than any of the previous slides, because we'll go back to them, but we can rewrite this. We expanded it all out, we made it all a bunch of things, and keep a note R, S, and R and SO, because when we go back here, we can actually see that these are in G of S and these are in G of R, but they're the inverse of each other. because of where the product shows up. So in the next point, we can just cancel them out. This product goes to 0. And then we just keep canceling, and you can do it. And if you want to do all the math, you can look up the Shmoocon paper, and they go through it all in explicit detail. And this leaves us with something really simple. E of GQ raised to alpha F1 plus beta F2 mod Q times x of V xv thing. So here's what you have to do. What's any number raised to the 0 power? Okay. That's all that says. I shit you not. All that says, if I make this all equal 1, it's true. Because what that means is if I raise each of these elements to the 0 power, because for each element in GQ, it'll all go to 1. And since I either have to find some random root mod Q, and Q is some huge number, and it's really hard to find a root for, and it's really rare, it means I solve the equation of x of v, the inner product of x and v. And that's all I want you to take away from this. Most of these things are, how do I cancel them out? How do I look at this and just make it talk to each other? And, oh, awesome. That was my setup key slide. But, yeah.
So it's a way to get a true-false answer?
It's a way to get an answer. So, in this case, we're querying on some vector. But theoretically, we can extend this into into the general field, or into pretty much anything. It just hasn't been done yet. Shmoocon came out in 2009. It's been 2-3 years since we figured out how to even do it on a vector. We have to build these technologies because they're new, they're rare, they're weird. And yeah, this is the key setup slide I was looking for so long ago. And I have 15 minutes left. My goal is to try and get you to talk a little bit about it. So what confused the hell out of you? What did you think? So we go back to this slide, because I didn't want to actually set up a talk for each of the things in this slide. And go, why are we so far back? Easy button? I know, I wish I had the easy button. But pretty much, we're going back here for the pretty much point of there's things happening. We have to actually look at crypto as if we can use the new. What are these, do you want to learn a little bit more about? What are the pairing things do you think you can do? Because I can go ramble on, but I actually wanted you, what's up? Oh, awesome.
Since you already know I'm dumb, I'm not afraid to ask this.
I'm an idiot as well, it's great.
So, all right. So, basically, I need this dumbed down to, you'll forgive me, the Rufus and Gallant or highlights version where you're trying to compare the objects. Let's pretend for a minute we don't know what's in the box.
Give me 1 moment.
Window to look in the box using these pairing tags, right? These algorithms.
Okay.
It's the goal here to try and find a way to match based on these numbers, knowing you found something inside the box. You're just not sure what exactly it is.
The goal is so I can ask you whether or not the equation I gave you and the token I gave you fit inside the box, I guess. Let's put it this way. Let me phrase this. So the way it works is I give you something that I encrypt. Okay? And I give you some equation corresponding to that encryption. I'm going to run this over, let's say, 3,000 things. I want you to tell me when does this equation equal, when does this number you encrypted match the equation which I gave you? Does that make more sense?
Yes. In other words, you're saying it sounds like what's being said is that given enough time, you can actually locate some value inside the box. Is that an accurate statement?
You can know whether or not the value which someone encrypted matches the window which you can open inside to the box.
What does Alice know?
What does Alice know? Alice is God. No, she. Sorry,
What does the answer?
I can't actually see you. Sorry.
Maybe the question that you asked. What does the result of the calculation done by Bob tell Alice? Does it tell her exactly which element was found? Does it tell her
So remember the inner product thing? I can construct an inner product to tell me anything about my item, pretty much. Okay? I can make it 0, 0, 0, 0, or some number 0, 0, 0, 0, something like that. Okay? When I give that equation to Bob, I can have him go whether or not these two things matched. I can go, did the inner product from this token and the inner product from this encryption match and cancel all out?
And what does that reveal to you?
It reveals whether or not that equation I first met. So, like, let's say I have 1, 2, 3.
Does that equation, okay, so
Yeah.
the equation might represent a value.
The equation might represent a value. It might represent a ratio between the values. It might represent some item that makes it all disappear and cancel out to 0.
So is this a fair statement? Like, Bob's got an encrypted database on
Yeah.
protein folding.
Yes.
Alice wants to run some queries, but she doesn't want to know Bob the query.
Yes.
Running. But she wants the answer.
Yes, that's pretty much, and it pretty much says, give me everything that returned is true to that query. Does that make, yeah. But without telling him what he looked for.
And not even letting him know what he returned.
Yes, he doesn't know what he returned and he doesn't know what he got out of it.
This doesn't really make sense given your case where you said with Pete, you said all he does is she attacks Bob and gets what Bob has, and then she wins.
This is assuming Bob is semi-trusted. Okay, sorry. This is assuming Bob is semi-trusted and in the KSW system. Remember I gave you two separate systems of KSW and SSW? In SSW, if Eve attacks Bob and gets all of the tokens back, she still doesn't know what she worked on and she doesn't know what the predicates mean. Inside of KSW, you can derive the value of the predicates by, if I'm looking for like the string urgent, I can encrypt thousands of strings, and if the first time one of them returns, I go, oh, she's looking for that. And then I can narrow it down based on that. Does that make more sense? Okay. Sorry, the lights are blinding me. I'm trying to figure out what time it is. You're good. I'm blocking out the light because I can't see you through it.
I was wondering about if this would be the kind of problem like the NSA would want to query the FBI's database, but not
Tell the FBI what they're looking for. That's exactly what this is. That's great. Usually it goes, I'm a remailer, encrypt something, send it to me, and filter on these rules. But that's pretty much exactly what this is.
Question. But, so go with his example, CIA wants to query FBI's database. Didn't FBI have to do a huge amount of work computationally and pretty much know the queries they were going to enable in order to create these tokens and give them to the CIA?
No, Alice, the person who holds the key, can make a token for any function which she deems that she can write in inner product form. Okay? So we... Not really. So you can actually do all the... So the reason inner products were chosen is because you can do a bunch of functions inside of them. And you can write the same thing in multiple ways, and you can have it cancel out in different ways, essentially. Okay? So what Alice can do is she can generate a token for any item inside of that inner product form that the FBI can then query on. The FBI has to do a huge amount of work currently because we haven't figured out how to do it quicker yet. And from there, Alice can pretty much write any equation she wants and just hand it to the FBI. And she can hand it whenever she wants. You can do this at any time. You can go, I want to add a new rule to my mailing filter, and give the mailing filter a new rule. That's why you can generate a token at any point. And, yeah, okay. Any more questions, comments? Yeah.
You alluded to maybe some limitations to inner product, like these operators are still not able to do.
It's more how complex they are to do. If you read the papers, they'll go over what each inner product query thing will do and how you can represent it and how it will do it, and it gets weirder. But pretty much the inner product operation will let you do most of the things you need to do. You're fucked. It's like going, if I got the AES key, I can decrypt the AES.
Once we get better, or once we get faster at this, what's the impact?
It means I can have a great file system I can have a really secure Dropbox. On top of that, I can have an even more secure key distribution system built on the Dropbox that I can update dynamically without telling anyone. And even past that, I can search and do all of these great things inside of databases. I can create smaller